mic'd on.
Alright, cool. And we're good. Alright, everybody. Welcome back. If you're the first time here, what we're basically doing is we are continuing to work through the basic electronics workbook from the good old RadioShack. We are on stream 5 of us trying to stumble our way through how this works.
It's a pretty good streak.
Yeah, it's pretty good. We're here every Monday. Genuinely around 5 to 5:30 is when we're going to start these streams, depending on whether or not we have to run off for beer, which thankfully we didn't this time, so we're actually on time. And this, for anybody that's new, this is our new, our actual RadioShack kit learning lab here that we have here. You can actually find these on eBay. I looked these up. I was curious. They're like $100 now.
Oh, wow.
It's crazy. There's a 3D printable model that you can actually build at home that maybe we'll get into it in future ones, which is kind of dope. But yeah, so thanks to everybody that's come. Feel free to jump in the chat. Let us know where we're messing up, if you have any questions, things like that. And let's get going. All right. You wanna do the reading today?
Sure, sounds good.
All right.
I think that's pretty good flow.
Oh yeah, we got some extra wires here. I was messing with it.
All right.
Let's pull these guys out so we start fresh.
So,
Cool. Do you remember where we left off?
I am actually trying to figure that out. So I do remember that we checked this chart here.
Yeah, we kept checking that. Okay. Oh, that's right. We were messing with the what is it? Potentiometer and the our meter gauge here.
Yeah, I'm not sure we got to below this area though. I feel like the last thing we did was check this chart. Looking at what we had there, it wasn't that complex. So I think we're now about to move into using resistors to divide voltage.
Okay. All right. Let's wait a minute. Are you sure? R1, R2, resistor 1, L26, V. Huh. Okay. Let's just go. If we're rebuilding it, we're rebuilding it. It's good muscle memory.
Excellent. And of course, it's always nice to practice. So
Yeah, let's do it.
All right, to begin, voltage dividers provide custom voltages in circuits. The formula is voltage out, V out, equals voltage in, V in, times R2 divided by R1 plus R2.
So 2 different resistors.
Yep.
Okay.
The circuits below use your learning lab meter as a voltmeter. And so it looks like, voltage is coming out. And that is equal to whatever the resistor 2 is resisting divided by itself plus resistor 1. So
so it's like chained resistors. Okay.
So just I guess if we're gonna just play with some numbers, let's say V out would equal voltage in. We're just gonna say that's 2 times. Let's do R2 as 2 and R1 is 10. It would be R2 divided by 10 plus 2 is 12.
12, right.
So we would have an equation that is V out equals 2 times 2 over 12.
2 over 12? Oh, okay. Got it. Okay.
Just, of course, these numbers are going to be a little bit more varied than that.
Yeah, no, I get it though, and we're gonna get a cheat sheet of all these things. I'm gonna have to study that in, know them by the back of my heart.
Oh, we definitely will.
All right.
And I'm sure this book will put our knowledge to the test eventually. They did say that they will eventually be losing these steps and going straight into
just
charts.
building it. Really? Okay. All right, let's do it then. What do we got?
All right. First step is to build a fixed voltage divider.
All right.
Fixed voltage divider is going to be created by first pushing the switch off.
It's off.
Absolutely.
Step 1, switch off.
Every time. Make sure that switch is off before you do anything. Step 2 Insert R1 across L26 and V6.
All right, what is R1?
R1 is going to be a 1K resistor.
1K. All right.
We're going to need 3 resistors.
All right. So
2 that are 1K.
2 1Ks.
And then 1 that is 10K.
1K. 1K and a 10K. Dude, having these little guys here, super helpful instead of having to dig through everything. And a 10K.
Interestingly, just as I was saying, they don't even tell us what resistor. They say R1 and R2, brown, black, red. Oh, it does say it right here. Never mind. See, that's
you
what
cheated yourself out of knowledge.
I did.
All right. Got our 10K and our 1Ks. All right. So what are we doing with the 1K again?
Okay, so the 1K, the one of them, R1, is across L26 and V6, which is our 9 volt.
So I got our 9 volt. Where's L26?
L26.
Oh, it means
LED.
I forgot that we're actually operating on a breadboard.
Yes.
Yeah.
We're now back to the breadboard. It's been a while since
it has. I'm like L. Looking around. All right. V6 and
L26.
L26.
Insert
1 and good. All right, there we go.
All right. Our next one is going to go from L27 and ground.
L27.
See, even I'm
is it also the 1K?
It is the 1K as well.
Okay.
So we were dividing. Oh. And according to our equation,
Ground.
by having these 2 1Ks here and dividing it by the 1K, we are dividing our voltage in half.
Okay. I'm going to have to figure this out as we go. I'm a man of seeing. I don't want to math in my head, all right? It's been a long day.
That's okay. That's okay.
All right. So what do we do next?
All right. R3 is across springs 2 and 64.
2 and 64. Spring 1. Nope. 2.
We're going to need a third camera for a
2.
page
Here we go.
for math.
That's a page for math? I don't want a page for math, dude. I just want to make cool electronic shit with my friends.
Well, math is awesome, actually. I've come to learn this.
You've been hanging out with your brother too much. Leave it to a physicist to actually
I know, right?
ruin.
Oh my god.
All right, cool. We are set. So we are between the milliamperes or whatever it is, milliamperes. So the actual gauge. And again, we're going to our photoresistor. I'm assuming we're just using that as a jump.
By the way, I did look that up. It is milliampere.
Milliampere.
But that's the English way. The actual French way, which is the guy's name, ampere, is ampere.
So milliampere?
Milliampere is how they would pronounce it.
Do you think that like other people that build electronics, when somebody comes up, he goes milliampere, and they're just like, "What a douche!"
Yeah, like
Why is he pronounce it like that?
Fancy food. You need to refine it a little bit. No, ampere is how we pronounce it over here on our side of the
Step 1, turn off. Step 2, question mark. Step 3, profit. I love it.
Absolutely. And I know that we make a joke about turning these circuits off, but if you're messing with real electronics, you're going to be messing with some extraordinarily high voltages and
fire.
Yeah, fire, and possibly even
fire bad
becoming the thing that closes the circuit. And you don't want that.
Oh, that's a good point. Yeah, death.
Yes, absolutely.
Fire bad, death worse.
So
right.
We are just messing with 4 double A's in this thing. So it's not really the
9 volts is the most that it goes up to.
Yeah, we might get a small fire, but in the real world,
fingers crossed.
You really don't want to be. You really want to make sure this thing is off before you mess with any electronics.
Fair enough. All right, so no fire, no death.
No fire, no death. Absolutely.
That's like step 2.
That's
and
our
step
new
3.
battle cry.
No fire, no death.
Step 1, no fire, no death.
No, step 1, power off.
No fire, no death.
Step 2, no fire. Step 3, no death.
So we need spring 1 to ground using a blue wire.
Spring 1 to ground. Blue wire. I think we're done with this thing, eh? Our old guy?
I think our old guys are. I think that thing could be retired.
All right, I'm pilfering from our old project here. All right, so spring 1 to ground blue wire. Nailed it.
All right, and next we have a yellow wire to spring 64, and I guess that's going to be testing our volts.
Yeah, so it's a jump again. So we're not actually using the photoresistor. They're just using it as like a bridging for our resistor there.
All right.
All right.
So according to how I think the math is going to work, we're going to be halving our output.
Okay, so where am I plugging this?
So push the power switch to on.
Okay.
Death and fire.
No fire, no death.
Touch the yellow probe wire to the 9 volt. It'll indicate about 8.4 volts.
All right, let's see.
Interesting.
9 volt. 8.5. Actually, that's
Okay.
closer to 9, eh? Yeah.
8.4, close to that. Okay, well, yeah, we do have some variance in ours.
Oh, that's right. It was a bit weird. I remember the last time. Ours
So
were off.
let's see. Touch the probe to the junction of R1 and R2.
Okay. To the junction of, so it's got to be L then, right?
Oh yes, we got to put it in the L slot, and now it'll be approximately halved.
Yep. And it is. We're like just shy of 5.5.
Excellent. Yeah, this fits the formula, which shows that when R1 equals R2, the output voltage will be 1/2. The input voltage of 1,000 divided by 1,000 plus 1,000 is equal to 0.5.
Gotcha. See? I don't need math. I just need visual representations of math.
Absolutely. And, we can even build ourselves a calculator.
Yeah.
And then we just, all right, fine, we built a machine to do it. Oh, man.
All right. Cool. What are we doing with our cool thing now?
So,
Turn off.
yeah, no fire, no death, absolutely. Well, step 1 for our next device is to push the power switch to off.
Beat it.
Absolutely. We're now taking R3. We're putting it across springs 2 and 64.
2 and 64. Already done.
All right. We are connecting spring 1 to the ground using the blue wire.
Done.
Okay. We are connecting springs 38 and 64 using the yellow wire.
38 and 64. Okay. Oh, we're going back to the potentiometer. Potentiometer? How do you pronounce that? You look that one up? Potentiometer?
Potentiometer.
Potentiometer is what I'm calling it.
Excellent.
How do you say it? Potentiometer?
Correct.
Oh, I actually got it on my first go.
Nice.
Yeah, potentiometer.
There it is.
As we're cracking beers.
Well, you gotta learn math.
I gotta learn to do a lot of things, including how to pronounce potentiometer.
Absolutely.
Cheers.
Cheers.
All right, we're good there.
Now we need 37 to voltage V6. That's our plus
V6?
9 volts.
All right, we do that blue or yellow?
That is a blue wire.
Perfect, because that's the only one we had. All right.
We're gonna need a red one as well.
There's a red one over here somewhere.
Rock.
I just didn't have the yellow. All right, and we're going 9 volts with it.
We are going to the 9 volts. That is correct.
Done.
Last but not least, connect spring 39 to the ground using the red wire.
Ah.
Oh, we're making it
All right.
this time. I am okay with that.
So why are we? See, I still don't fully understand why there's 3, right? So this is going directly to our resistor. It's going to the positive. So this is coming in through. It's going through our 10K, right? Which is controls and make sure that we know what this is actually a factor of, right?
Okay. Right.
But then,
Look.
oh, that's going to the ground.
We know some of these symbols. Look at this. This is an extra one. Do you think maybe maybe these first 2 are just the raw values, and that middle one is our?
Oh, this is going to allow us to fluctuate it.
Right.
Got it. Okay, this makes a lot of sense. All right, so we're going to turn it on.
Push power switch to on, and rotate the potentiometer knob while watching the meter.
Oh, yep, there we go. Check it out.
The meter voltage is highest when the knob is rotated toward spring 37, which goes to plus 9 volts. Interesting. Okay, so
as we're going...
that goes up. There we go.
Yep.
Definitely.
0.9.
And you know what's interesting? Well, wait, no, we don't want to mess with the voltages in. Remember, the resistors can become damaged.
All right.
Or even the meter ourselves. So, yeah.
Look at I'm a DJ.
Absolutely.
I'm starting to realize you say absolutely when you're just like, this fucking idiot. Every single time. You're like, absolutely. Yeah, good job.
Absolutely.
All right, cool. All right, so so we got the voltage coming in. It goes up to the top piece, right? Then this is a resistor in here. And we're pumping that out. And then the 10K one puts the...
okay, right.
How do you pronounce it in the French?
Yeah,
milliamperes.
Milliampere, yeah.
Milliamperes. It's it's just the milliampere. That's weird though. Why would we need to ground it still? Like, why is this going to the ground? That's what's throwing me off, right? It's because we already, if you look, the whole circuit goes.
So
like,
I'm
we're
thinking
good here, and then they already grounds it on the other side of the.
So I'm thinking what happens is that the power comes in through here, gets pushed this way, comes around, and so when you close the circuit towards that direction, it closes the circuit using the potentiometer.
So it sends the rest on the ground.
Yeah.
Got it. Okay. So by not grounding it, we're basically pumping in power. We're stopping it. We have a potential, without doing it, to damage the potentiometer.
Without a ground, we'd probably cause some damage, maybe even a fire.
I think they had us do that before without grounding it.
Maybe they did. Perhaps we had to feed it through to a different circuit.
Maybe. I can't remember exactly.
I do recall when we did once use a spring just to pass a signal from one wire to another.
It could be it too.
For sure. They definitely use this in interesting ways.
I am curious though. If we drop this back on L, are we going to get half of... Yep.
Oh.
I thought so. Okay, so we're just
Even
reducing
further.
the power. Let me pull that out. Pop that in. So there's our 9.
Yeah, there it is.
And then the 7.5. Yep. And 3. Yep. Okay. Okay. It all checks out. Let me turn that off before I fry some.
Well, here's a brain teaser for you. For us,
Is it
I guess.
math?
It is.
Fuck.
So, with your V in is 9 volts, your R2 is 10K.
Yeah.
What resistance is R1 if the V out is equal to 6 volts?
Okay, if it's 6, and we have 10, it's 6. I don't know. Fucking.
Alright, let's see.
I need a piece of paper.
Well, let's see, 9. So we need to essentially get the math that makes 9 into a 6. So we need to take 2/3 of the 9 in order to make it volt. We need to take 1/3 away in order to make the volt out.
Couldn't we just grab the equation and just like... Oh, shit, we have a whiteboard
We absolutely can. We do have a whiteboard. Alright, so the equation... Do we have any markers?
Yeah, I got things. Hold on, let me grab it.
Here's some right here. Permanent.
Permanent. Those are permanent. Yeah.
So, learn as we go. Probably might have to introduce a whiteboard to you guys in the future. Learn as you go.
Alright, got the dry erase marker.
Absolutely.
Alright. We don't have a camera over at that though.
No, we do not. So we're just going to have to be loud and proud.
Alright.
So we're looking for V out is equal to V in.
VO equals V in.
What's the next part of the equation?
There's a
It'll
division.
be right in the middle of the page right there.
Where are you saying this? Oh.
Yeah.
Okay, times
Okay.
R2 divided by, and then in parentheses, R1 plus R2. So R1 and R2 are 1K.
Okay, so VO VI is R2 is 1K.
Yes. R2 is 1K, right?
What's on the bottom? It's the brain teaser all the way on the bottom.
Oh, here we go. If
Just don't
9
read it.
volts and R2... Oh, I'm sorry. It's changes. R2 is 10K.
Okay, R2 is 10.
10K, yep. What resistance is R1 for V out equals 6?
Okay, so R1 plus 10. I'm just going to assume the K's there.
Yep.
So, in order to make V out is equal to 6.
Oh, 6. Okay, so got it.
Alright, so if we know anything about actual math,
Yeah, so we can add... PEMDAS?
PEMDAS.
PEMDAS. Wait, it wants R1 though?
It wants R1.
Okay. So then just take fucking 9 and you should be able to multiply those guys together. 9 and 10 makes it 90. So 6 equals 90.
So 90 divided by
R1 plus 10. Yep.
Okay.
Then subtract 90.
So we have 86 is equal to minus 86 is
Yep.
equal to
R1 plus 10.
R1 plus 10.
And
Okay.
then minus 10, right? That's not right.
That is incorrect.
Yeah, I fucked something up there.
Alright, so let's take a.
Why are you making me math, man? This
Well, because we gotta be.
we're gonna end
engineers.
this series.
You gotta be engineer.
Fucking done with it. Wait. Oh shit. See, I don't know how to do this with the parentheses and the values inside the parentheses. To become like
So what you
division.
want to do is now you're gonna be 90 divided by R1 plus 90 divided by 10.
Right. Okay, that's what I'm
And
missing.
6 over there. So we're gonna do our little. Let's see, 90 plus 86 equals. Oh man, now I'm done.
No, hold on. So 90 divided by 10.
Is 9.
Yep.
On that side.
And then it becomes 90 over R1.
So 90 over R1
Plus 9.
So we're going to
Subtract 9 on the other
subtract
side.
9. That gives us minus 5 is equal to 90 over R1. So now we got to do times 90.
Times 90 on the other side.
And
that should wipe it out, make it positive.
So, well, it's actually negative. So that's going to be 450 is equal to R1. And that still seems wrong.
No, because it's a fraction, that's why. So you take the 90, it gets divided on both, or gets factored on both sides, and then we should end up basically just flipped out with 5. I think it just makes it positive on the other side too, because the 90s will wipe each other out. So then it becomes positive, is it 5 over?
It's just
5 equals R1? What, is there an answer in there?
R1 equals 5.
I think.
I
Yeah,
think you might
should
be
be
right.
5K. Is there an answer? Where's the book? Where were we?
Bottom section, I guess.
Bottom section is 24. Oh, here we go. Answer equals 5K. Yeah.
5K, there we go.
Okay. I'm not doing math anymore. Let's.
Well, you know what? To be honest, that's kind of awesome. We just figured it out.
Yeah, like fumbling 3-year-olds.
Hey,
I hope
I
your
gotta
brother's
help my
watching
kid with
right
this.
now and he's screaming.
I had to help my kid with this, so this is good for me.
I don't have to help my kids anymore. I need them to help me. I've reached that point in my life. All right, cool. So 5K.
Hell yes.
All right. Yeah. We're gonna need to just basically spend an entire thing just doing math.
I cannot wait. Actually, that was a lot of fun.
You had fun with that?
I did have fun
You're
with that.
a fucking psychopath.
I did have fun. So blame the beer. I agree.
Yeah, I mean, I'm definitely gonna 100% blame the beer. It's the easiest route, and I'm definitely gonna stick with it. All right, what do we got next?
All right, next we're going to connect resistors in series to increase resistance and reduce the current flow.
Okay, cool. All right, so instead of halving it, we're gonna do a series.
Oh, I get it. Yeah, definitely got to blame the beer for sure.
Yeah, blame the beer.
This is a new time.
What's
guy.
that?
It's a new time chat.
Oh, cool. Nice. All right. What else we got?
The total resistance of two resistors connected in series is the sum of the individual resistances. The formula is total R equals R1 plus R2. That's
Easy math. Why can't it all be that?
They should have started there. That's how they do it.
You have
in
like a
school.
1K, and then you have another 1K resistor, and that's 2K's worth of resistance.
Bam.
That's about the level of math that I would feel like doing.
Yeah, that's yeah.
All right, what else?
So we're gonna build a circuit to test two resistors in series.
Okay.
The first thing we're gonna do is
Turn it off.
no death, no fire,
No death, no fire.
and we're going to disassemble what we have, I guess.
All right. Disassembled. Cool. We had the 10K. I'm assuming we're using 3 resistors again, right?
We are using 3 resistors. We actually are only using 2 resistors.
Okay.
We need 2 10K resistors.
2 10K.
Those are brown, black, and orange.
All right. I'm putting the 1K guys back. And we already got a 10K right there, so I'm going to keep that out. I'll grab the other 10K. Put that guy on there. Where's our 1Ks? There they are. All right, cool. 2 10Ks. Got it. What are we doing now?
We are now taking that R1, we're crossing it to V6, or 9 volts,
Okay.
and J26.
The J26.
So I think we established this last time. I'm only going to say the number of volts.
Yeah, no worries.
That'll help us anyway later when we're trying to do the math.
J26. Bam. Done.
Okay. R2 across J28 and T28.
Okay. Go in your hole. Go in your... There we go. Got it. Okay. Got it.
Spring 1 to ground using a blue wire.
Spring 1 to ground.
Potentiometer. Oh no, milliampere time.
Milliampere time.
Milliampere.
Milliampere. Ampere. Oh shit. Did I bend that? I probably bent that. It's fine. Don't worry. It's fine. These things are meant to bend.
They are.
I don't know if that's true. I'm just doing it.
I mean, they're wires.
Alright, if it's... Fuck.
Now
Okay,
connect
we're good.
a
All right.
yellow wire to spring 2.
Done.
Alright, that's going to be our probe.
Okay, cool.
So push the power switch on and touch the free end of the yellow wire to the junction of R1 and R2.
Okay. So we're going in J then.
Absolutely.
Got it.
The
We're at
meter-
9.
Yeah, it says it'll be about 0.84 MA, but
Yeah, this one was always off a little bit. So that makes sense.
so we're going to move the yellow wire to the free end of R2 at T30.
Yep, and it halved it.
All right, awesome.
Cool.
Since the current is halved, the test proves that resistance is doubled when 2 resistors of the same value are connected in series.
You know, that'd be super useful if, like, wherever, like, hey, we need a 10K and we don't have it, but we have, like, 5Ks. We could just put 2 of them together and just, like, run them. It's 10K, right?
A whole series of ones. You know, actually, I bet you there is a reason why you might want to do that.
Yeah, because if you want to do that, right? Let's say that you were trying to run 10K, like, so if we had something that we wanted like 9 volts actually hitting it, so we would kick it right here, and we get our 9 volts, right? So like if we had that going, we have our current going in, we have the 1 resistor, and we're like, okay, yeah, we want 9 volts off of everything that we're basically spiking off that, and then you just add this one. Maybe we want like an LED that's like a soft LED. We don't want 9 volts. We want like less.
Right.
So we just toss it in there.
So you then have you basically use the resistors themselves to almost break off.
Yeah, little pieces of it. Actually, I'm kind
Absolutely.
of curious, man. I'm gonna.
Oh wow, no, that's interesting.
I'm gonna mess with something.
Okie dokie, hell yeah.
All right, so I'm gonna do. Oh shit! Power off. All right, so I got a green. Okay. So I want. Oh, I probably gotta go ground though, eh? Like I gotta close.
Yeah, because you gotta shunt some of that. It can't just go. Well, I guess it can just go from one end to the other as long as current passes through it. It ought to.
All right, so long side's the positive, right? So I'm gonna throw that bitch right in there, and that's gonna be I. And I'm just gonna close this gap off real quick, because I'm gonna ground that.
Yeah, just send it to the
So
ground.
I'm gonna take.
Oh no, you don't want to send it to the ground because it'll just cross the LED and then disappear.
No, it should stay. Oh, because no, what I'm gonna do is I'm gonna close that one, and then I'm just gonna take this guy. I'm gonna put him on T. Right? And if I did this right, and if I'm thinking correctly, which I probably am not, this one, they should both light. Yeah?
Huh.
Maybe? Is this the...
It might, yeah.
They should both light. This one should be brighter than this one. Let's see.
I believe it.
Oh,
And there
shit!
it is. Awesome,
Let's
bro.
go!
Awesome.
Okay, cool. Sick. So there you go. That's a perfect example.
And that worked wonderfully, actually. It was nice color on those.
Hell yeah.
Hell yeah.
So yeah, maybe you want like a softer light, right?
Fortunately,
But you also want like this
see.
is like a power light and this is like a connected light, right? So like you want the power light to be bright, but maybe you want like the other one
right to
short.
just let you know that
like an onboard light or something.
for sure.
So then yeah, throwing a resistor in there and you can regulate the power that you're getting so that you're not frying out components based off of what they're supposed to have.
Oh man.
Sick. Okay,
That is
cool.
sick.
All right. I'm starting to understand this, but fucking I'm not doing
And
that.
they say resistors connected in series, so I imagine if you sent a resistor across like the circuit board, the breadboard, using some wires, that still is connected in series, right?
Yeah, because that's what we just did, right? So we plugged it,
Right.
we plugged the one in, and we plugged it in the same channel as J, so it's getting the same power. Each one of these, like it's basically in series. It's no different than like if we were touching these guys together,
Right.
Which we I don't want to. No fire, no
But
death.
if we were, yeah.
Yeah. So it's like you're touching it. So you're basically just running these things in parallel at that point here. You're saying, okay, here, give me the 9 volts, but here, go through this other resistor and then just give me the half, the 4.5 or whatever it was. So I'm like, okay, that makes sense. Cool. This is all coming together. I feel like I'm actually learning something.
So
This is kind of dope.
So now I'm actually realizing that these resistors can be connected in more than just a series. Say you have a this connector here,
Mm-hmm.
right? And you're bringing your power off of that. You're getting the full 9 volts that we're looking for.
Yeah.
So that power comes off of there. So imagine if you have another wire that leads more power in to this one.
Oh.
And gets halved on that end. So now we just have like a quarter of the amount of power or not a quarter, 3/4 of the amount of power that's shunted off, not 1/2.
What do you think happens if we throw more power into it on that side? So like we got, oh shit. Okay. This is going here at T. Yeah, let's do it at T, right? So what happens if we like chuck in more power into T? I don't know if I want to do this. I'm curious. Where'd we end up? 4.5 on that?
Yeah. We're gonna see if we get
give it 1.
Only cut out 1/3 of that. Or 1/4 of that, I mean.
If I put this here, it's gonna go like way up, right? What the fuck?
Not only go. Yeah.
We just put more power into it. Why did it half?
We just put more power and it's still halved. Holy interesting.
I don't understand that.
What if you touch it at the end? I
Down
don't
here?
think it would do anything, but I just...
Whoa, it was angry.
Let's avoid
Okay,
that.
because that's because we're not running it through any resistors,
And
and
we're just
that
getting
we
raw
just
voltage.
we just threw basically like 9 plus
Okay.
1.5 volts into
So
it.
now imagine if you had a resistor that was, what have we got here? Two 10Ks? Two 10Ks?
It's free. See what's up.
So if we had a...
I think it's just giving it 3 volts. Plus a little bit more. Like if I do 6 here, right? Is it just gonna bring it up to 6? It is.
Oh, interesting. Okay.
I don't understand that.
I don't know.
So if we pump in 6 volts on the other side of that, it will... I don't get that.
Well, think about, we're doing 6 and 9, so we're supposed to be, we should be expecting 15 total.
That's what I thought, but we're not getting it. It's dropping it down to whatever voltage we put in. Like if I put 7.5 here, right?
Right.
And I put it into that same channel, we're a little bit over.
Huh.
All right.
That is pretty interesting.
We're gonna have to get to that point at some point. I'm lost again. I
Yeah.
think if we drew some of this shit, we might understand it.
So I'm thinking that, let's say we have this receiver here, or resistor here, and we had this as a 10K. If we had this as a 5K, do you think it would be 5K and then 10K? Or do you think it would be mess up the whole thing?
If we put 10K where?
Say we have two signals parallel.
Yeah.
This one's going to be 10K, 10K.
Yeah.
This one's going to be 5K, 10K.
Oh, you want to change this to 5K?
I want to take another resistor and put it parallel to it so that they both feed into this resistor, but from 2 different points.
Oh, I see what you're saying.
And
Is it the 5K?
Yeah, and I want to know if that will change things. And we might...
I think we're going to set shit on fire. I think that's what's going to happen.
What we could do is we can take this receiver, or resistor, what do we keep calling a receiver, and flap it over to the A, and then we'll take a B and bring it down to J. And then we'll take a wire and we'll plug it into accordingly.
Okay, so we're doing power off.
So let's
Okay.
get a 5K resistor.
I don't think we have 5K resistors in here. We got 4.7. You want a 4.7?
Sure. We should be expecting just, it's a simple equation, R1 plus R2. So we should
Okay.
be...
So here we go. 4.7. And where are we doing it?
We're going to run it in parallel. This one's going to be pulled out and put in the A slot.
Okay. And then we're taking some from the A slot and throwing it into where?
And then we're going to take, and this is an additional, what size was that one?
4.7.
Okay, so we're going to take it from the B slot and send it to the J.
There's no power though.
And then we're going to take a wire and apply power to both. So we're going to take a wire from 9. We're going to put an A here or whatever.
Well, it would have to be in this side because these are each their own.
Oh yeah.
So
That's why.
you want one in. You want one in.
We're going to test.
A.
We're going to test the first one first.
All right, so let's go
We're
A.
going to see what the difference is.
Okay, so that's
our
like
half.
4.5.
Now we're going to put it in the B slot and see what it changes.
Okay, so that's 4.5. Right. Okay, so it brought it up to like.
Okay, so if you did
That's
have
our 5K. Right? What did we have in there before? 10Ks?
we had 10Ks.
Okay, so that's our 10K plus a 4.7.
So
That's
now
what
we're
it's
getting
supposed to be.
14.7 resistance instead of 20K resistance, and as we can see, we're resisting less just by having 2 different channels that go to the same secondary resistor. Right?
I see what you're saying. So you want, it's basically just comes down to like piping it through different resistors.
Yep. So now you don't
In
even
parallel, so you don't need the extra one. You could just route, depending on how you want to do it.
multiple to the same.
To the same.
Yep. So now if we had like this 3-point or like a multi-switch
Yeah.
or something, each switch could go to a different resistor. Maybe
Isn't that kind of what this thing does?
right? And so it can kind of turn an LED from brighter to dimmer.
Got it.
Essentially added like a dimming switch.
Oh, well, that's what the potentiometer is. I imagine that.
Sure, but we're not doing it mechanically.
Oh, okay. So it's fixed. It's like
Yeah.
option A or option B.
Absolutely. We're giving it a designated sort of...
I like that.
Oh, man.
That's cool.
This is exciting stuff, guys.
All right, cool. All right, we messed up
My
all of our
brain
shit.
is
All right.
stoked.
Let me put the 4.7 away. All right, what do we got next?
All right, so now that we've built a circuit to test two resistors in a series, we're going to go ahead and rearrange the resistors in the series circuit.
Okay.
We're going to see what happens. First, we're going to push the power switch to off.
It's off.
No
No
death.
fire, no death.
No fire, no death. We're going to take R1, well, they're still the 10Ks. We're going to put that across J26 and 9 volts.
Okay, 10K, 9 volt and J26. Basically putting it back where we got it. Okay, got it.
Rearrange, don't you know English? R2 across M26 and the ground.
M26?
M26.
All right. Okay.
We're going to connect spring 1 to M30 using a blue wire, and spring 2 to J30 using a yellow wire.
M30
M30, spring 1.
and J30. Okay. We don't have any power running through anything. Oh, yes, we do. I'm sorry. We have one of the resistors pulling in from the 9.
Excellent.
Okay.
So we're going to go ahead and push the power switch on, fire and death. The meter will indicate about
Half.
0.42 with our tolerance.
In our milliampere.
Milliampere. The same.
Never not going to say it with that stupid French accent. No offense to any listeners, or if you're French, it's not your fault.
Well, if we pronounce it the German way, it might be more accurate.
How do you? Oh, is it German?
No, ampere is French.
Ampere.
And
Yeah.
the French made the metric system.
What's the German way?
I don't know. Ampere.
Ampere. All right. Anyway, sorry. Moving on.
Oh, man. So this is the same current as in the previous project.
Yeah.
This proves that the current flowing through a series circuit remains the same even when the resistors are rearranged. So it really just was showing us that you can put them in any order and it will do the same thing. We just experimented and discovered that even if you put them in a different order, you can utilize that different order, but ultimately, yeah, it produces the same thing.
I still don't understand that shit. Because now they're not even.
Oh, these ones are connected in series. They connect from the volt
But here,
to the channel,
this is what's.
to the ampere, to the channel, to the resistor and out.
Okay, hold on. I'm going to turn this off. I'm just bypassing that second resistor. That don't make any fucking sense. All right, so this is what's throwing me off. We have our volts coming in, right? It's going through the 10K resistor. It's then actually going into our milliampere, right? That was the worst French accent ever. All right, so milliampere. It's going in here, right?
Yeah,
then the negative's coming back out and feeding
into a resistor.
afterwards.
Right, so the resistor
After
is now
a reading.
resisting after the fact.
So this is what's throwing me off. Maybe it's where my brain goes, right? Because logically I'm like this, then this, then this, then
I
this.
think I know why. Because
the whole circuit?
Because it's only shunting half of the power out to the ground. It's resisting half of the power on the way out to the ground. We are measuring.
No, but so here's what I mean.
So
this is what I mean, right? We have the 9 volts coming in.
Mm-hmm.
So in my brain, I'm like, okay, volt in, hitting the resistor, then it's going to the meter. So the meter should have the 9 volts, right?
Right.
So in my brain, I'm like, it should just be the 9 volts. There's our 9, right? And then it's going to ground. But even in that scenario, I'm like, okay, after you've already taken your measurement, right?
Right.
After you've already done that, then I'm going to have a resistor after the fact. I feel like it shouldn't have impacted it, but
so
it
I think I
does.
understand this, actually. So what happens is it's not a how much we currently have. It is an active measurement. So it's constantly measuring the amount that's flowing right now. So let's say we have, the power is going through from the one resistor, from the power to down the resistor.
Mhm.
It's going into the milliampere. It's coming out the milliampere, and it's coming to this resistor, and only this much is being resisted. So this one's saying, hey, you are currently operating at however much is not being resisted, because what's being resisted is being sent away.
It's still behind it.
Mm-hmm. So it's saying
it's like taking water out of putting stuff into a cup, but like what it's measuring what's left.
It's measuring what's left. Absolutely.
Got it.
Yeah.
Okay, that's gonna take. Okay, this is the problem with like trying to do this while coming from a logic-based like programming piece, like
No, this
Power Automate or
is
something.
really awesome. I'm actually having a lot of fun with this.
It's measuring how much is left in the
Yeah, because
actual
it's an
milliampere.
active measurement, not a
It's an
passive
active
one.
measurement.
Yep.
Got it. Okay. Okay. I get it. Thank you for helping me with that.
It's a weird sort of thing to think about. But,
It's so
but
odd,
once I was
yeah.
like, oh wait, no, this is because the energy is constantly flowing. That's what we're measuring.
It's measuring the flow,
Mhm.
the flow of it.
That's a better way to put it. Absolutely.
Okay.
For those of you guys at home, again, if you know a little more about this than we do, suggestions are always welcome on how we can sort of.
Anybody
refer to
wandering
these
off the
things, or-
street knows more about this than we do. Just so you know.
They probably poured through this book 82 times. We've just
Probably
started.
just rewired their house, man. I know some copper strippers that probably
Man.
know this shit better than we do. All right.
Oh man.
We have
So,
adult.
are we-
Yeah, we're fine.
Yeah,
We're fine,
I hope so.
Yeah, no, we're good. It's gonna be the weirdest Twitch band explanation ever. We were talking about stripping copper wires and drinking on a stream while working with a RadioShack electronics
You know,
kit.
something like that.
Uh,
All right. Well, our next task is to connect resistors in parallel to reduce resistance and increase current flow.
okay,
All right.
so what are we doing?
We are going to. The total resistance of two resistors connected in parallel is the product of the two resistances divided by their sum. The
Okay.
formula is total R equals R1 times R2 divided by R1 plus R2.
All right, hold on. I'm writing it on the whiteboard.
I'll be right back.
What? You gonna write it?
Oh, I'll be right back.
Okay. Wait. I need the formula.
Oh, I'll help you with that.
All right.
Total R
Done.
is equal to R1 times R2 in parentheses.
Okay.
And that is divided by R1 plus R2 in parentheses.
Got you. Okay.
I will be right back.
All right. R1. All right. I don't know why. I wrote this as like a string, but I should have just written it R1 plus R2 in parentheses. Okay. We're going to have to get another camera. If we're going to keep mathing like this, we're going to have to get another camera. It's going to be unfortunate. All right. Just be stepping away for a quick second. We'll be right back. All right, we're back. Cool. All right, I wrote it on the board. So R equals R1 times R2 in parentheses divided by R1 plus R2 in parentheses.
Awesome.
All right, so what are we figuring out?
That is a total amount of resistance. Actually, yeah, if we want to do this before we go ahead and get our board going, we are going to be using, for R1, it's going to be 100K.
All right, so I'm going to write 100.
And R2 is 100 as well.
Okay, times R2, which is 100. All right, so that's 10,000, right? 100 times 100? 10,000?
Yeah.
All right, 10,000 over, and what are we? We're 200?
Oh, yeah, and this is an easy equation.
So over 200. And 10,000 by 200 is what, 5,000? Or 500 rather?
500, that's correct.
Okay, so R equals 500.
R would then equal 500, so we would have 500K resistance at the end of this.
Okay, shit, look at that, mathin'.
And that's what we get for parallel resistors.
500K?
Damn, dude, that's awesome. Huh. Wow. Okay.
All right, you're going to have to go home, because I already know you. You're going to go home, and you're going to start looking up all this math. You're going to have to make me a little cheat sheet, and then we'll just throw it up there as like a cheat sheet for all this
That's
stuff.
going to be awesome. I'm definitely going to need to get all of these equations going.
All right. So I'm assuming we got something we got to build, right?
Yep. We're going to go ahead and have two resistors in parallel, which means they're going to both take a load of the circuit and recombine them.
Oh, you said we're working with the hundreds, not the tens.
100K.
All right.
For those of you who have the triple striped resistors, that is brown, black, and yellow. We are way too high speed for that.
High tech. We got extra colors, bro.
Absolutely, yeah. Colors you ain't even seen.
All right, 100Ks.
100Ks.
Got them queued up.
The power switch is off.
Power switch is off. No fire, no death.
No
All
fire,
right.
no death.
What we got?
Insert R2 across V6. Oh, that's our 9 volt, sorry.
Yep.
And J26.
J26. J26 to 9 volt. Done.
Okay. So, one lead of R1 into J28. Leave the other lead disconnected.
Ah, okay.
Interesting.
Yeah, I don't think we've ever left the...
I've never...
All right, I'm going to turn it on. You touch it.
Okay, yeah, will do.
What's the next thing we got?
We're going to connect spring 1 to the ground using a blue wire.
Done. Bam.
Shunting power straight from the box right to the ground. Just losing it. Connect spring 2 to J30 using a yellow wire. Excellent.
All right.
All right. Interesting. We're going to push the power switch on. The meter will indicate about 0.08 MA using our measurements, probably 1.2. Insert the free lead of R1 into a 9 volt breadboard hole.
Just any hole?
Into one of the 9 volt breadboard holes.
After I turn this thing on?
It calls for fire and death.
All right. Let's turn it on. If I swear to God. All right.
It will indicate about 0.08.
Yeah.
Excellent. So insert the free lead of R1 and handle that thing. Bare fingers. You got your conduit.
We're good.
Into a 9 volt breadboard hole.
Just any one of the holes.
Any one of them.
All right.
No, double on you.
It did it?
No, into the 9 volt.
Oh, into the 9 volt.
Yep.
Okay.
Pull power.
Oh, right. Yeah, because we're running parallel, right?
Yes, we are. Oh, and the other one's connected into the 9 volt
And
already.
it doubled it. Yep.
There we
Okay.
go.
That makes sense. All right, cool. Yeah, so now we're at 0.2. So that makes sense.
It does, yeah, it doubles it. Okay, that makes a lot of sense, actually. Huh. Because if you look, the R equals 500K is exactly 1/2 of the 10K.
10K.
Well, yeah, the 10,000 right there.
Oh, the 10,000 that we get on the top of
the
like the
10K.
multiplying resistor 1 and resistor 2.
Yeah, the 10M, I think. Right at that point.
Right, but 500K is the resistance.
What is, yes. So essentially, what it seems like we're reading is that if we were,
we're fucking dumb. It's not 500K, it's 50.
you are correct.
It was easy math up until I looked at it. Yeah, it's 50. It's 50K.
Yeah, now I'm looking right at it.
Which makes a lot of sense now. Because if it's 50K and we're pumping in like the 10,000 initially, this makes a lot of sense. Our resistors are 100K, right?
100K a piece, yeah.
Yeah, this makes a lot of sense. Okay, cool. So we're basically just pumping in. We're pumping in.
So if it sounds like we don't know what we're talking about,
It's because we fucking don't know what we're talking about.
Yeah, it's because we absolutely are learning. And this is what's awesome about this is, this exact process. The fact that we are now learning.
Feeling like you can't do child math?
Well, I guess learning how to dust off the cobwebs is part of the process for sure.
I'll take that. All right, so basically what we're doing is when you run things in parallel, you're just basically increasing the amount of, well, in this case, we're increasing the amount of voltage that we're actually piping through. So that makes a lot of sense. The reason why we're sitting at the point is because instead of using the 10K resistors, we're using the 100K. So that changes the scope of what we're actually working with in this.
Yeah.
So this makes a lot of sense. So when I didn't have this plugged in, right, and if we're operating at 100K, that makes sense because now we're at 50K at that point instead of like out of the 100Ks instead of it being like a one. So then when we pump in the other one, it's going to dump in the additional, which brings it up.
So if we were to swap that out for...
This makes a lot of sense because now we're at 200K.
So here's an interesting thing. If we were to swap one of those out for 10K, do you think that the...
Well, we should be able to do the math on it, right?
Well, we absolutely should.
All right. Turn this off.
Do you think we get to point, or do you think we get to like the full 0.8?
So which one are we swapping? We'll just do R1. We're going to swap that out. We're going to change that from
R1 is the second
100 to 10.
Okay, so
10 times 100 equals 1,000. Right?
Yeah,
and then it's 1,000 over, which will be our 10. So R1 plus our 100, which puts us at 110. Right? And then what's 1,000 divided by 110? It's, what is that? Fucking...
We just did that to ourselves, didn't we?
What?
So we just did that to ourselves, didn't we?
Well, it's something 0.5. I think it's 10.5. Or no,
like 0.9 actually.
this is fucking stupid. 0.9? No, it should be 0.5.
Well, if you think about it, if you take 10 110s, you're going to get 1,100. If you take 9 110s, you're going to get 99.
So I'm taking out my calculator because this is the future and I don't have to do this in my brain anymore. Divided by 110 equals 9.09.
Cool.
Yeah, so 9.09. So if we do it that way and then, okay.
So we should be facing 9.09K resistance. So we should be actually looking at almost exactly on the milliampere what we are putting into it through the volts.
I don't know.
Divided by 10.
Let's see. All right, we're going to swap one of these out for a 10. Oh, I just lost one. All right. It's off. Okay, it's off.
No fire, no death.
No fire, no death. All right. We toss this back into the 100 before I lose everything. I think I just lost one of our other resistors on the board here. All right. I'm going to turn this on. Just individual right now. We're at 1, right? That's because we're on 100K.
Right. So
this should
we're
only
reducing
move
to,
it like tiny bit.
I think it's going to move it a lot because now we're not resisting 2 times 100K. We're now only resisting 9.09K.
Right, but we're still operating on 100. We're on a scale of like 100K, right?
You might be right, yeah.
So let's
Might be the same thing as the 10 amp situation.
So there we are there, and I'm just gonna run this in. Oh, you had it right.
Right,
it's
that's
a 9
what
volts.
I was thinking. Yeah, and it's going to be just a little bit less.
I think I did it again. I think I'm thinking about the amount of flow going into it, or
the amount we have rather than the
instead
amount
of
we're
the
getting.
flow. Yep. Man, I gotta wrap my head around that one. All right.
Oh.
I need a light bulb moment, and us drinking and fucking around with this board isn't really helping it right now.
Well, eventually we're going to be working on making these into actual projects.
Yeah,
so I think
something tells me I'm
super awesome.
gonna need to walk around with the fucking fire extinguisher.
Yes, absolutely. But now we're going to be able to, again, as you said, make dials that make LEDs light up in brightness, so we can make boards and stuff, cool things for the BitHaven Hackerspace.
All right,
absolutely.
I like it.
So I think that'd be pretty cool. I think we.
Are we at time?
I think we're actually right on time.
What time is it?
Well, our next subject, it is 6:15. Our next subject would be to deal with potentiometers. So it's a whole new subject.
All right, we can end here. I need to rack my head with this stuff.
Yeah, I think I was about to say, I think I
annoying.
really do need to take a look at what we have here. Maybe consult some of the engineers, electrical or otherwise, in my family or in my group, and get some proper schooling, because this is crazy. I feel like we've been on session 5, and now we're actually using the equations that we're learning.
I think at the end of this, I think once this has got to be the annoying part, right? Once we wrap our head around this shit, I think this is where, once you have it like that light bulb moment of understanding, I think the rest of it's just going to be pretty straightforward.
Yeah, we're at the vocab part of learning language.
I
Eventually we'll be writing poetry with this stuff.
That's a poetic ass way to go out. All right, cool. Well, thanks everybody for watching. Sorry we stumbled through it. We'll try to figure out something, if we're going to stick with the math stuff, to get on camera more. So that way you can follow around as we mess up not only the math in our head, but the math on the paper. And again, thank you all for coming. Hopefully you learned something. I'm sure you guys picked it up faster than we have, but hopefully we'll come back.
Yeah,
I got some takeaway and some homework to do. So awesome. But
exciting.
yeah, super exciting. All right, thanks again, guys. We'll catch you in the next one.